Ele não tá no professor físico. Vou falar aqui para começar o. Deixa eu ver só. Pelo menos um minuto aí. Okay, into the season. So I think we can start. So it's my pleasure to introduce to you Professor Gabriel Landi. Professor Landi is an associate professor in the physics Department of Physics and Astronomy at the University of Rochester in New York. And he's also an editor for Physical Review Research. So if you want to complain, you can talk to him. He was an assistant professor in Brazil, that's where we met. First at UFABC until 2016, and then he moved to the University of São Paulo, where we overlapped, and he was there until 2022. So Professor Landi heads at Rochester, which does theory research at the boundary between quantum information sciences and statistical physics. He's a specialist in the field of open quantum systems, with applications to quantum thermodynamics, quantum transport, and quantum metrology. He was he became an affiliated member of the Brazilian Academy of Sciences in 2020. Gabriel is one of the best people to talk about physics broadly. I was just talking to him last night about, I guess, quantum metrology and the Lawrence group. So you can see that he is really into everything. So if you have a chance to talk to him, please do. He's a fantastic speaker and a fantastic scientist. And we're very excited to have you here. So please, Gabriel, take it away.
Okay. Hello, everyone. Good morning. It is my absolute pleasure to be here. I really want to thank George and the organizers for this invitation. It's really glad that I'll be able to present some of the work that we've been doing over the past few years in Rochester. So what I'm going to do here is I'll kind of present this talk in chronological order, like how I got interested in the topics. And I think this might actually be kind of helpful for the students to see how research evolves and changes over time. So I actually want to start where things started for me. Let me see if this works. Of course it doesn't. There we go. For me, it all started with these questions about the thermodynamics at small scales. And this is actually, the kinds of problems we're interested in. Imagine that you're trying to do this with a RNA molecule, right? So this is actually an RNA molecule, and you use optical tweezers to stretch and compress a molecule. Now, what is special about a molecule? Well, it's small, and therefore it is subject to Brownian motion, right? That it's wiggling because of its contact with whatever solvent it is. So if you now ask the question, how much work does it take to stretch a molecule? That answer is random. Every time you repeat your experiment, you get a different amount of work. This is where it all started. And this can actually be measured. This is one beautiful experiment which measured the work distribution of stretching and compressing an RNA molecule, right? So we have now fluctuations in something that is really thermodynamics. And this was really huge because for many years, people always thought that thermodynamics belonged to the macroscopic world, right? Thermodynamics is about big systems, classical large systems. And we didn't really bother to think too much about thermodynamics at the small scales. But this is one of the fundamental results that shows that you can think about thermodynamics at the small scale. But there's a caveat. Thermodynamic quantities fluctuate. Like for me, this was huge. I loved this. I thought it was really, really beautiful. Here is another example. which is also quite interesting. Suppose you're thinking about heat exchange, how heat flows from one body to another. We all learned that heat always flows from hot to cold. This is how Clausius formulated the second law of thermodynamics. We can write this mathematically, introducing a concept called the entropy production, which is for this specific problem of heat flow, is this quantity is the product of heat times the difference in temperatures or inverse temperatures. And then what is nice about this concept is that we can now formulate the second law of thermodynamics as a mathematical bound, which says that the entropy production must be non-negative. Entropy can always be produced, must always be produced. And this is really cute. I love this result because you see, it says that whatever sign Q has, Q can be positive or negative, meaning flow can go this way or that way. The sign of Q has to be the same as the sign of whatever is in here, right? So if you the sign of Q will follow the sign of the temperature gradient, right? And this is how we interpret the sign. Now, this is also, a nice example of classical thermodynamics. Can we do the same thing in the micro scale, right? So this is one of the early experiments when I was just starting the field. We played around with just theoretical models of heat flow in two spin chains. We have two spin chains. We prepare one of them cold, one of them hot, and we look at how heat flows, right? And heat fluctuates, so we can measure the fluctuations or the distribution of heat in the spin chain. This is as a function of time, and the different plots refer to different sizes, right? So you see that for very small sizes, you get a lot of wiggles, but as the size of the chains become larger, you get this kind of smoother Gaussian, right? And so this gives us an idea of how you transition from a macroscopic heat flow, where heat always flows from hot to cold, to a microscopic version, where now, if you look at it, there is a small probability that you actually get heat flowing in the wrong direction, right? You can locally violate the second law. You can cause heat to flow from cold to hot. It's a random process. You can't really control it, but sometimes it happens. Now, these results, they were huge in the 90s because of a series of fundamental discoveries by these authors, which I, of course, have a very biased opinion, but I think this is absolutely like Nobel level material. I think it's really, really an important discovery, is this thing called fluctuation theorems, which is this discovery that if you look at the distribution of these thermodynamic quantities, if you look at the statistics of these thermodynamic quantities, they actually have a relation between whenever the quantity is in the right direction, so to speak, and whenever it goes in the opposite direction. So, for example, here I'm writing this in terms of entropy production, but you can do the same thing for heat or work. These results, they say that the probability that you observe a violation of the second law is connected to the probability that it flows in the right direction with an exponential suppression, right? And so now you can have violations of the second law in the microscopic world, but they are suppressed when the entropy production is very big. So that's why, we don't see them in our day-to-day activities. Sorry?
What does it mean by a minus sigma representation?
You mean, what does it mean in terms of units? Or
Sigma is a contribution per scale.
so this is like the probability that, you observe a heat that is minus 20, how it's related to the probability that heat is plus 20, and exponential sigma. It's just that sigma is dimensionless, so there is no units in there. And so this result, it kind of explains why, we don't observe this kind of behavior, right? Why this clearly means that the video is being played backwards, because, this is an event which has a huge entropy production. A coffee mug is falling into the ground, it's splashing, the entropy production is huge, and therefore it becomes very, very unlikely to observe it in backward order. So this is kind of where I started. And then there was another result that for me was really, really eye-opening, which is this result by Esposito, Lindenberg, and van den Broek, which showed how you can formulate the second law of thermodynamics purely using information theory. And I thought this was absolutely mind-blowing. So here's the basic setup. You have a quantum system, which is prepared in some quantum state rho, S, and you couple it to some environment that is prepared with some state rho E, and you allow them to interact unitarily, right? This is kind of very basic interaction between two systems. Now, if you think about it, this actually is super, super general. This describes a huge class of processes. This could be a qubit and another qubit, or this could be, your frying pan, and this is the water coming from the sink when you want to cool down your frying pan, right? It doesn't matter. It's two systems that are interacting unitarily. And when they interact, of course, in this latter example, it would be a very, very complicated Hamiltonian, but still, this is what it would look like. And the important thing is that now a system, it interacts with its surroundings and they become correlated. They go into a state that is not a product state, it's correlated. And so what these authors showed is that the entropy production of this process can actually be written as a contribution of two terms. The first term is what's called the mutual information. It's a measure of correlation. It tells you how much did the system become correlated with the environment in this interaction. And the second term is called the quantum relative entropy, and is a kind of a measure of distance. It measures how much did you push the environment away from equilibrium. So I like this very much because it's very operational, right? It says that essentially entropy is produced and nature becomes irreversible whenever information or energy flow into degrees of freedom that you don't really have access to, right? So if a coffee mug falls into the ground, right, we can apply unitaries on the coffee mug, but we can't really apply unitaries on the ground, and we can't really apply entangling unitaries between the coffee mug and the ground, right? So our degrees of control are limited. We cannot, the environment is something that you can't really control. You can't really do stuff to the environment. And that's why things become irreversible, because you have energy and information flowing to degrees of freedom that you cannot really access. So one kind of interesting application of this that we studied concerned the process of relaxation. Now, here's how we might think about relaxation. Suppose you have a system and you allow it to equilibrate with its environment, right? And suppose your system is a qubit. Then essentially what the environment wants to do is to impose some kind of thermal populations, right? The Gibbs distribution, the Boltzmann weights. If you prepare your system in the ground state and you just let it be, it's going to slowly evolve to a state that has some populations. If you prepare it in the excited state, it's the same thing. So this is the system being forced to adjust its populations because the environment wants. In addition, you also have another effect, which is that if you prepare your system in a superposition, right, it's something that now is not just ground or excited, but is ground and excited, then this superposition is also going to be washed away. This is the process of decoherence, right? And so thermalization in this sense can be thought about two things. One is the system adjusting populations, and the other one is decoherence. All the quantum features being washed away. One of the very beautiful things that come out of that previous result that I just showed you is that the entropy production can be very neatly factored into your contribution that only depends on the adjustment of populations and a contribution that only depends on coherence. So we can think that a process is irreversible because it adjusts populations and because you lose coherence. And this introduces a new feature that's not really present in a classical theory, which is a dissipation without the flow of energy, right? It's irreversibility due to the loss of information, but not necessarily due to the loss of energy, right? So he puts information on a pedestal as a kind of a fundamental thing together with energy in the quantum. My group, together with many other groups around the world, we've been working really hard on trying to formulate the laws of quantum thermodynamics and understanding deeply what does quantum thermodynamics really mean and is it useful for anything. And we've approached this with this same kind of mindset that a lot of the quantum 2.0 community uses, which is to take a critical, a fresh, and a detailed look at things that sometimes we've taken for granted, right? So things that maybe we've overlooked in the past, let's kind of dot our I's and cross our T's kind of thing. And when we do that, we find some fundamental challenges in trying to formulate a properly kind of comprehensive theory of quantum thermodynamics. And I wanted to go through some of those challenges. Some of these will be very basic, some of these not so much. So we start with what is heat and work. If I had $1 for every time someone brought up this question in a quantum thermodynamics conference, I would maybe have a few dollars. But it's a common thing. In thermodynamics, we divide energy like this. We say, look, the internal energy of the system, it can change either because you perform work on the system or because heat flows between system and environment, right? There's heat and there is work. Now let's do the same thing using the rules of quantum mechanics. We say we have a system and an environment. They have a Hamiltonian that looks like this. There is the Hamiltonian of the system, of the environment, and an interaction between them. And we want to do work, and we think about work as maybe, a time-dependent drive. So we want to shake the system or drive it with a laser or something like this. Now we go back to our quantum mechanics textbook and we look at the Heisenberg equation for the evolution of an observable. And it says that the ddt of the average of O is its commutator of the Hamiltonian and its kind of intrinsic time dependence. We apply this to the operator O being the Hamiltonian. H commutes with itself, so we only get this. And now we open this up by using the fact that H is this sum of these three terms, and we get this equality. So this is energy conservation at the level of the unitary dynamics between system and environment. So now, let's see if we can interpret things. Well, this is the change in energy of the system. It kind of makes sense that we think that this is the internal energy. Green is the change in energy of the environment. It might make sense that we think that this is heat, right? Because it's the change in energy of the environment. And this term is the change in energy of the system that is due to drive, to the fact that you're shaking the system. And if you were not shaking, this would be zero. So it kind of makes sense that we think that this is work. But then what about this term, right? This is the change in the interaction energy between system and environment. Where does this belong to? Is this part of the system? Is this part of the environment? It's neither, right? Because energy is not a local thing. Energy is not this plus this. Energy, there's also the energy of interaction, right? And what should I attribute that to? Is that a heat? Is that a work? Right? So it kind of becomes weird and a little bit ambiguous. In classical thermodynamics, this is always avoided. Because in classical thermodynamics, the interaction energy is always much smaller than the energy of the parts, because usually interaction energies depend on the atoms in a surface, and energies of the bodies depend on a volumetric thing. So classical thermodynamics, you never see this. It's not really an issue. But here it is. It's very simple. But what do we do with this? And how do we interpret these things? This is the law of conservation of energy that comes from a quantum mechanics textbook. But if we want to attribute a thermodynamic meaning to it, it kind of becomes a little bit weird. It becomes a little bit ill-defined. Here's another basic problem with quantum thermodynamics. Suppose you have the following experiment, very common thing to do. You have an atom, has a ground state and an excited state, and you drive it with a laser, right? So the Hamiltonian, you're going to shake it with a specific laser drive with some specific frequency. And you do this very well. So you do this resonantly, for example. And then this means that if you start in the ground state, after some time, the system will just Rabi oscillate and be in the excited state, right? There's no bath here. There's no heat bath. There's only a laser that is driving your system. So any change in energy has to be work, right? And so this would be an example of a work injection. You have used photons of the laser to take your atom and drive it up. Essentially, you're charging up the atom like a battery, right? That's fine. Now let's think about the opposite problem. Suppose we start in the excited state and we do exactly the same thing and unitarily rotate the atom from excited to the ground state. This is kind of a work extraction because the energy of the atom went down. You reduce the energy of the atom. But where does this energy go to, right? I mean, it goes back into the laser, it goes back into the electromagnetic field, but you don't really catch that photon, right? It's not a useful thing. So there seems to be a very, very big asymmetry. You need this laser with like a gazillion of photons to charge up a single atom. But when you discharge that atom, that's just like a silly photon that is, you don't really use it for anything. So you know, in classical thermodynamics, we think about work as something that, you know, if you say lift a weight, and then that's definitely a good energy that you store that you can then just use it to, you know, perform work on something else. But in quantum, there seems to be kind of a bigger asymmetry here. So that's also something to. I'm always cheating, but why?
Because of the big laser, right?
Yeah. Yeah.
So there's some extra material outside. So is it really a closed system? Because if the laser plays into the equation, then of course the right-hand side starts to make sense again, right?
Yeah, you're absolutely right. And definitely it is cheating, but it's just to put a little bit of perspective on the fact that what does a thermodynamic cycle means? For example, you know, we think in thermodynamics about an engine and a refrigerator as being kind of opposite operations. But I would argue that a quantum refrigerator is still pretty useful, but a quantum engine is kind of silly, right? I mean, you don't really, the energy that you need to pump the laser is, of course, way higher than the energy you would get out. But you're right, it's not a super fair comparison, just to put things in perspective, yeah. Finally, there's another issue, which I do find to be a bit more fundamental. So I want to go through the following protocol, okay? So suppose I want to ask the question, how much does the energy of a system changes when I apply a pulse? So I do this. I start in a quantum state psi. I apply a unitary U, some kind of pulse. And this will take me to a new state, psi prime, which is U times psi. And I ask the question, how much did the energy change? Naively, I would say, well, you know, initially I can say that the energy was, you know, the average of the Hamiltonian on psi, and then, you know, in the end is the average of the Hamiltonian on psi prime, and that seems like pretty reasonable. But how would you actually measure this energy change? How would you do an experiment, a single experiment, okay? So where you go and you say, I want to measure how much the energy of my system changed, right? How would you design such an experiment? Well, this started in 2007 with this paper, which introduced what we now call the two-point measurement scheme. That is a very common technique. And as the name kind of implies, because this is a change in energy, you technically have to measure a system twice. You measure it before and after you apply the pulse. That's how you calculate the delta, the difference, right? So the protocol would be something like this. You have a Hamiltonian, it has energy eigenvalues and eigenvectors given like this. You measure the energy of the state psi. So you do a projective measurement on this basis En, and this will give you outcome En with probability given by the Born rule. But now, and this is the key bit, because you measured En, your state collapsed, right? You have the measurement back action, so your state has to change to be updated from psi to En, right? That's the rules of quantum mechanics. There's nothing we can do about it. Now we apply our pulse, but we are now applying the pulse not to psi anymore. We're applying the pulse to U. And then all we can do at the end is measure the energy again. And so now, again, according to the Born rule, we'll obtain outcome En given by this. And so what you get is you get a joint probability. It's the probability that in these two steps, you get En and then En. And so this is just given by the product of the two probabilities. So now you have this data, these two energies. How do you construct the average change in energy? Well, the naive thing to do would be to say, look, in the end, in the second experiment, I obtained En. In the first one, I obtained En. The change in energy is just En minus En, but I have to average this over my many experiments. If you do this, you will not get this, right? You don't, because of the coherence, because of the fact that the first measurement destroyed your state psi. You will only get the same thing if your state psi was already an energy eigenstate. So any coherence that you have in psi is destroyed, right? So this is, I believe, is kind of fundamental, right? Because does this object even make sense? Should we even be thinking about this kind of object if we can never really measure it? Right. So sorry. So this is what I just said. So you know, how do we interpret these kinds of things? So this is a very kind of a serious challenge if we want to come up with a theory that you know gives us useful results and meaningful ways to interpret the energetics. Okay, so where do we go from here? I have recently, I turned 40 this year, so I'm officially in my midlife crisis here, which means that I can, become very grumpy and start questioning random things. So I've recently started just questioning some of these approaches that myself and many others in the field have been taking. And I think in particular that we should become much closer to experiments. I have always prided myself at asking questions in a way that's kind of platform agnostic, experiment agnostic. I think that these questions, they really only become meaningful if we focus on specific experiments and understand what is energetics at the quantum scale in these specific experiments. And so I think by doing that, we can ask questions such as what is actually work? What is in thermodynamics, work is useful energy and heat is like useless energy. But what does that actually mean in quantum experiments? What is a reasonable thermodynamic task? Like I just mentioned, I think refrigeration is pretty cool, but a heat engine seems kind of silly. And also, how can we measure these things? What does it mean to measure thermodynamic quantities and assess this topic? So I'm proud to say that my group have not answered a single one of those questions yet, but we are working together. So to do that, the approach that we've been taking has been a lot more data-driven. We now take the stance that we never see a quantum system. No one ever saw a quantum system ever, right? All we see is data. All we see, we measure a quantum system, we get data, and we have essentially bit strings. And the questions that we want to ask is, how do we interpret thermodynamics based only on data? So our starting point is always, what is the data? What is the measurement? And what can you say about thermodynamics based on those measurements? And I think this is honest in the sense that it allows you to ask thermodynamic questions that can actually be assessed in it. So in particular, I will focus here on some of the results that we've been studying in the context of a particular kind of experiments called quantum jumps. So quantum jumps, they're related to, it's called a quantum master equation, which is essentially a system that interacts with the environment, and you can describe it in a way that in addition to the unitary dynamics, you also have this dissipative dynamics that is modeled by a set of operators L, which are called the jump operators, right? So this describes many systems. I'll give some examples in a second. But the basic idea is that such a master equation like this description, it describes an ensemble of trajectories, but in reality, what you really have are quantum trajectories, which look something like this. The system is evolving kind of smoothly. It's kind of walking around in Hilbert space. And then every once in a while, it might suffer a jump, a sudden jump, and it will abruptly, transition from one configuration to another, right? And these jumps, they occur randomly. And it's always like this. Some unitary dynamics, and in between certain jumps. Now, this kind of process, it doesn't happen in all kinds of systems. It was initially studied a lot in the context of quantum optics. And you can imagine that these jumps could be, for instance, a photo detection, right? So suppose you have a cavity and there's a photon that leaks out of the cavity. And when you hear a click, it means that a photon definitely left the cavity. You say, well, that's a jump. That's how it started. There are also other platforms that that can be described by quantum jumps. One that I'm particularly involved with right now are quantum dots or quantum dot arrays. And so this is one example of experimental data that can be used to infer quantum jumps from a quantum dot experiment. So let me just take a second and explain how this kind of experiment looks like. So these are, for example, silicon or some semiconductor material that you lithograph, and you create a little island, and that island can have either 0 or 1 electrons, right? You tune your voltages such that it will have at most 0 or 1 electrons, and you couple these two dots to wires, to metallic wires, and you do so in a way that electrons can tunnel from these leads to the dots and vice versa. And the electrons can also tunnel between the dots, right? So there's also tunnels. We like to keep things very simple, and we think about these problems in what's called a Coulomb blockade regime. which essentially just means that we exclude the possibility of having 2 electrons total. So that's not too hard to do because electrons repel each other. So if the dots are kind of sufficiently close to each other, there will be a huge electrostatic repulsion for shoving 2 electrons together. And so in the end, your system can operate in a scenario which only has 3 quantum states: a state where the dots are empty, a state where you have a single electron in the left, and a state where you have a single electron in the right dot, right? And that's one of the kinds of systems that we've been thinking about. And what is very nice is that you can continuously measure and obtain the quantum trajectory of the system, like it's shown here. This is actual experimental data from the group of Natalia Ares in Oxford. The way that people do this is using something called a quantum point contact, which is another kind of circuit element somewhere right here that you monitor the current through that element, and it gives you indirect information about the quantum trajectory of the system. This is how you can get a quantum trajectory. So this is actually a current through some device, but this current, as you can see, it has essentially 3 well-defined states, and we can now associate these 3 states with these 3 possible configurations. So we can map this current into the dynamics of this system within this Hilbert space. And what is interesting about this example is that we can also associate, we can, in kind of a one-to-one fashion, we can link to specific kinds of events. And in this case, there are 4 events. The events are the jumps, right? There are 4 types of jumps that can happen. You have, they've been labeled injection left, extraction left, injection right, extraction right. And that's exactly kind of the idea. They mean essentially events where an electron tunnels into or out of the left or into or out of the right. So we can use this kind of data to infer the quantum jumps that the system might undergo. And so now we start thinking about this problem from a thermodynamic perspective. We have these trajectories, we have these bit strings. The data for us is a sequence of symbols, right? It's a symbols which is, you know, injection hot. Oh, sorry, sorry, there's a typo here. H should be L and C should be R. Apologies for that. But essentially you have a string like this. This is your data. And you now want to ask some thermodynamic questions about this. Like, what can you say? If you have nothing else, I just give you a gigantic string like this. What can you tell me about the thermodynamics? Can you say something? Can you reach any conclusions just by looking at these strings? That's kind of the problem that we were thinking about. And the answer is yes. We can identify thermodynamic cycles from this problem. For example, suppose that this left lead is hotter than this one. So this is hot, this is cold. And we imagine a sequence of 2 jumps, which is like this, and then this. Yeah. This is what we associate with an engine, because essentially what you're doing is you're extracting chemical work. In this case, it's chemical work in the sense that, you know, you're shuttling electrons across a voltage gradient at the expense of extracting some energy from the hot bath and then dumping the excess into the cold bath. Sometimes we might also observe the opposite sequence, which is a refrigerator, something that goes like this. This is cold, you get some energy from the cold bath, and then you dump the excess into the hot bath. So you're causing heat to flow from cold to hot, but you do this at the expense of consuming chemical work. And finally, you also have the not so funny cycles, which we call the bounces, which is just when nothing happens. You have an electron that kind of tries to go through, it just tunnels here, then goes back and nothing happens, and you reset. So by doing this, we can go from a bit string of jumps to a bit string of thermodynamic cycles. And I thought this was actually quite interesting because we can now start asking different questions. So we can change kind of the flavor of the questions, and we can ask, for example, you know, what's the probability that you observe a cycle of a given type, right? This is all random. Your machine is not going to operate like an engine or a refrigerator. It's always going to operate like everything, but you know, you have to ask this probabilistic, which cycle is more likely to happen. You can also ask questions about waiting times. How long does each cycle take? And also, are cycles correlated to each other? If you observe a cooling cycle, does this mean that the next one is more likely to become to be a cooling cycle again or not? And so on. And so this is some example plots for this kind of system. This would be a waiting time distribution to the probability that it takes a certain time to complete each cycle. These are the probabilities of each cycle happening, average cycle times, and these are measures of intermittency. So essentially how often does, uninteresting things happen between interesting things. So we can characterize the full statistics of this, and we also came up with a nice formalism based on this idea of quantum instruments, which is a generalization of quantum channels, and I'm quite impressed by how powerful this turns out to be. So if anybody wants to discuss the mathematics here in more detail, I'll be happy to.
Sorry, do you have an understanding of what happens if you were to increase the system? Like what would happen, this description, imagine that instead of having, you said 2 quantum dots or something, imagine you have a bunch.
Yeah.
So what happens, if you try to take a thermal limit?
Yeah, so that is a good question. We haven't looked at that in this specific scenario. We've looked at it in other scenarios, and then in those scenarios, what really matters are the kind of the energies here. So if the system has, like, for example, all of the sites have the same energy and so on, there's usually ballistic propagation, and then it doesn't really matter if you have 2 or if you have 100, the physics is pretty much the same. If you have different kinds of on-site energies, then you can get funny stuff. Yeah, but we haven't looked at that specifically for this kind of problem. Okay, so now in the last few minutes that I have, I just wanted to switch gears a little bit and say that, we've been playing a lot with just kind of going back to classical a little bit, or incoherent descriptions, and studying systems in the optics of what's called classical master equations. And this was largely motivated. There's this beautiful experiment from the group of Simone Gasparinetti in Sweden, where they have 3 transmons, so 3 superconducting circuits that they use to create a refrigerator. And we were really kind of blown away by these results, and we realized that, what they have is a very kind of interesting system, but can actually be described by a fully classical description in terms of classical master equations, provided that you use your perturbation theory to calculate rates and so on. So we scaled back a little bit to classical rate equations, and the reason for that is because in a classical picture, it is much easier to understand what is going on. So the way I think about it is like you're talking about how a system navigates in Hilbert space, and Hilbert space is systems can kind of move around continuously in space, but a classical master equation is the limit where the system only jumps between specific energy states, right? So it doesn't Rabi oscillate from here to there, it just jumps, right? So you have a few energy eigenstates. For this model, it was a 5-level system that they had. And you just think about these trajectories, but the system is jumping up and down in Hilbert space. And so it's kind of like what we call stochastic excursions. It's like you have a system of states, and you're asking about how the system navigates into these different states. So I'm going to skip this bit, and I want to use this idea of classical equations to just discuss this last result, which departs a little bit from thermodynamics and goes a little bit into metrology. So because we have this kind of classical master equation description for these processes, we can think about these trajectories as just a system jumping up and down between a discrete set of states. And so we got into a little bit of a rabbit hole of, okay, how can you use that for timekeeping? So I have a trajectory, I have my data, my bit string, and I want to keep track of time using that. So this is where our rabbit hole led us. Suppose you're in a deserted island and you want to cook some fish, right? But you need a clock. How do you construct a clock that can tell you when your fish is going to be done? The sun is not a very good idea because the sun moves too slowly. You're not even going to see it moving. The sun is, it's precise, but its resolution is very, very low. So what you might do is you might look at some stochastic process. You might look at counting waves, for example. You can say, one fish is equal to 250 waves. That's my standard of how many waves does it take to cook a fish. Or you can look at heartbeats or something like this. And so the question that we asked was, okay, I have a master equation. I have, rates and the system is jumping up and down. What is the best clock that I can make based on my data being this string of symbols? So the data is just, the symbols where the system is. And you can see a system, random states. Or you just have a bit string of random stuff. What is the best kind of estimator that you can build that will give you optimal time precision? So we want to build an estimator, some kind of function, theta of x1n, which is unbiased, meaning on average, it gives you the time, that is the thing that you're trying to estimate, and it also saturates the Crumerel ball. So it turns this inequality into an equality. And what we found is that the estimator is actually very simple for a master equation. It's just, you just have to count how many times the system visits each state. So you just see, there's a trajectory, you see how many times it went to state 1 and 2 and 3, and you divide by the rates, the escape rates of those states. These gammas are the escape rates of these states. And this is actually the best way that you can estimate time with stochastic data. And this is just a kind of side thing that we can also calculate the Fisher information exactly for this time. And this was interesting because actually timekeeping and thermodynamics, they have a very close relationship with each other because there's a lot of results out there that show that there's a thermodynamic cost to timekeeping. So we view timekeeping as kind of a nice application of thermodynamics, and we're kind of excited to have this result, which kind of mixes everything. And then to finish and to put things a little bit in perspective, I wanted to show you a video. So that was regular speed. This is slow motion. This is one of the turbines of a hydro power plant back in Brazil. This is almost a 3,000-ton thing, right? This thing spinning here is around 5% of all of the electricity produced in Brazil. This little thing, right? And I like this because I think it really puts in perspective, we're talking about thermodynamics of small things, and this is where thermodynamics really shines, is in the big things, and the contrast between the two, I think it's really interesting to think about. So with that, I conclude. I want to thank the DOE for funding, and also most of the works that I showed here were done by Guilherme and Abe, who are PhD students in our group, and also in collaboration with Pedro, who's now in Marseille, Casper and Patrick, who are in Basel, and Mark, who is in London. And these are the basic references. And I mean, thank you so much for listening, and I'm happy to take any questions. Thanks.
Thank you, Gabriel, for this very interesting talk. So we have time for other questions. Yes.
So you showed us some of the classical, Markov focus on it, right? So is there a way to quantize that? I mean, you can just put the same generator and to solve the raw and get that thingy and have the same numbers, or something you ever thought of? I mean, just quantifying the classical data by allowing mixed densities for the states.
Yes. So one of the things that we sometimes do is you think about the data as a register, and the register itself is a quantum system. And then instead of thinking about it as stochastic dynamics, like the one I was showing as a stochastic dynamics of the system, you can actually describe it as a deterministic dynamics of system plus register. And that is actually quite convenient. And their state becomes what's called a quantum classical state that has kind of specific correlation properties which are kind of useful to use.
Yes.
So in the first part of the talk, when you define the thermodynamic process, do you need to assume the degrees of freedom of the environment?
Sorry, I didn't hear the last part. Do I need to assume what?
So in the first part of the talk, when you define the quantum thermodynamic process, you need to assume the degrees of freedom of the environment much larger than your subsystem.
Yeah, so that's a great question. So this leads a little bit to the wrong way, to the interpretation of some of these results. So this result, sorry, right? So this result, for example, right? I think it's a beautiful result. It does not assume any of that. Your environment could very well be a qubit, and your system could be whatever you want as well. that being said, there's a bit about the interpretation of things. If your environment is just a qubit, this will give you a number, right? It's going to give you a number, and it's going to be a non-negative number, so it satisfies the second law. But like, what do you get out of that number? What does that add to your interpretation? It's not as much as if your environment is macroscopic. So what I'm trying to say is that a lot of the results here, they don't need to assume that the environment is macroscopic or has some specific structure, but usually you only recover like the nice interpretations of thermodynamics in that limit.
So, if the environment is small, it's not really reversible behavior, and the entropy production is only held in a specific time period. I mean, if the environment is small, there is no real irreversibility emergence.
No, that's a good question. I think I disagree because if you think about it, I like to think about irreversibility as a very operational thing, meaning what kind of unitaries can you apply? What do you have control over? So if I have a system and an environment, they're both qubits. So this is a qubit, this is a qubit, but I cannot apply any unitaries here, right? And I cannot apply any 2-qubit gates. I can only apply unitaries here. Then you get an effective emergence of irreversibility, right? It's the same as when you do the partial trace, right? And you do a partial trace and you calculate a reduced density matrix. That's an irreversible operation because it means that, if you look only at the reduced density matrix of say, the system, you're assuming that you can't really control the environment. I don't know if that makes sense. Yeah?
Are there other questions? Yeah.
Can I ask a question about the experiment or
Yeah.
I understand the experimental results, but what is your specifically did you quantify the jump probability as a function like the temperature difference or conclusion for it?
So the question is more like, what can we actually conclude about this?
Yeah, or by analyzing the history, can we say something about the probability, jump probability that E or IL as a function of the temperature difference or chemical potentials or
Yeah, so I mean, we can calculate anything you want from the perspective of both a steady state, which is how people usually do things. Like usually, the basic thing would be to just ask what is the average current that is flowing. So that we can do, and we can also calculate things from a kind of a single shot or probabilistic level where we say, what's the probability that you observe an event that is, for example, right? In terms of temperature differences and chemical potential gradients and so on. So we can do both, and kind of what I showed here is that you can also combine these things to think about probabilities of cycles that give some thermodynamic interpretation. Was that the question?
Yeah.
Other questions? If not, I have one. So he's saying that one of the things that this field is doing is trying to understand again and revisit standard statements that we know from thermodynamics and trying to put in this quantum thermodynamics context. But what about things like, for example, the fluctuation dissipation relations? So for example, if you try to do, normally you learn, like the Einstein relation between fusion and temperature, things like this.
Yeah.
But you could also have tried to do things, not just with 2-point functions, but higher order point functions, 3, 4, and 5. Normally these things are very hard to do because it gets complicated to map how fluctuation dissipation works in higher order point functions. Recently, it's been understood that there is some global symmetry that actually dictates how fluctuation dissipation actually connects and maps the different Green's functions into the others. Do you know if there is any, so what is the, for example, my question is, concerning the fluctuation dissipation relation, so in this kind of operational point of view, is there any new development in trying to understand these sort of foundational issues relating fluctuation and noise?
Right. There are actually. I can even show you later on. There's one very interesting paper where, for example, they look. So in the fluctuation dissipation relation, you have some average, which is related to some variance or some fluctuation. That you can actually take that fluctuation and you can kind of decompose it into something that is related again to like kind of more classical, related to populations, and something that is related to some information theoretic measure of non-commutativity or coherence. And then you can understand how does coherence actually play a role in say the fluctuation dissipation relation, right? And which I think it's pretty cool interest, cool idea.
Okay, so like there are just pieces of the normal Einstein relation.
Yeah, so I would say, you know, it's usually I think a lot of quantum thermodynamics is like revisiting traditional StatMech results, many body results, but trying to look at them from a more information theoretic point of view and a more kind of critical idea of like what am I actually measuring, what is really going on in a finer brain set.
Okay, if there are no other questions, thank you, Professor Landi again.